Okay, so welcome, folks. We're continuing our traversal of material related to double categories, double theories, double models, and ultimately double instances, but with a sojourn to support that into profunctors. Um, and today, uh, the sojourn will bring us back into discussions of double categories. And per request, last time we'll be looking at some examples of use of profunctors, which are in fact rooted in double categories or are employed in the double category context. And this material will also provide a later jumping off point for a bit of discussion of another highly related categorical construct, namely that of a sliced category, which turns out to be very useful for understanding the role of uh, profunctors and double models of discrete double theories. But much of our attention the past few sessions have been on profunctors. And my goal is to reconnect us with that, remind you of some of the essentials, emphasize a few points which bear it, and arguably were underemphasized before, and use that to look at some of these examples of profunctors, which several of which will tie in directly or indirectly to our needs with Cat Collab and double theories, double models. So to do this, I'll turn to my slides. And we'll get going. Okay, so we've talked in recent sessions, our previous sessions, on this profunctorial topic about profunctors as ways of turning summaries of getting from A to B into summaries of getting from A prime, where A prime is upstream of A, to B prime, where B prime is downstream of B. So given that we know how to get from A to B, we can know how to get from something that A prime, where we can get from A prime to A, and then follow the thing from A to B, and then go from B to B prime. And we talked about how a profunctor from a category C to a category D, while it's useful to think of it as its own type of construct, and in some sense as a generalization of a functor, as a bridge between these categories, category C and category D, it does boil down to a functor, a plain old functor, from the product category of C op times D into set, where this op it reflects the fact that we're considering coming from something upstream of A prime, upstream of A, whereas in D we're considering things that we can get to from B, something B prime we can get to from B. And we've been looking at collages as a way of illustrating. So these sort of collages where we have a category C and another category. Here it's shown as D. We'll be dealing today with some words not C. And where profunctors link from one to the other. They may have an object here that can go to multiple such objects over here, or go to none at all. And that reflects the fact that for a given C and a given D, this set could be empty, or it could be quite large, indicating there's many ways of getting from C to D or none at all. And I noted that profunctors we're very familiar with are Hom profunctors, which go from C up to C. And where set here is just the set of morphisms from C to some object C in category C to some object D in category C. So a profunctor summarizes ways of getting from A to B, or ways of producing a B from an A. And we had talked last time about the relationship of this to functors. And I had noted that with general covariant functors, if we have something that takes a B and gives us a B prime, we can lift that. If we have a functor like the maybe functor, we can, and it's covariant, we can lift G to go from maybes of B's to maybes of B prime. So F of B to F of B prime, if F is covariant. And in Haskell, this is captured with F mapping G over the maybe. Same thing with list, right? We can lift something that can map an int to a bool to something that goes from a list of ints to a list of bools, right? And the same thing for the reader functor. And I highlighted last time that, well, this is true, this covariance. If we have something goes from B to B prime, we get something goes from F of B to F of B prime, is true for covariant situations where we actually have a B to do something with in F of B. There's a class of functors which are contravariant, where we don't have something to deal with. We have a kind of a hole for something. We're waiting for an A to be given to us. The A is the input, not something we have at hand to map. And I noted the contravariance here. So if we have something that goes from an A prime to an A, so from an A prime to an A, we can lift it to go from this sort of contravariant functor from F of A to F of A prime. So even though this is from A prime to A, we lift it to something that goes from A to A prime. And this is characteristic of contravariant functors. And the reason I emphasize this is because with profunctors, we are operating with one part of it that's contravariant, the first element, which needs something. It's where you start. It's where it's the thing you produce from which you produce. And we have something that's covariant, the thing that we produce, the thing that we go to which we go. So when we think about lifting here, there's one part that's contravariant, and there's one part that's covariant, the second component here. And here, you may recall that while with covariant things, if we have something that goes from B to B prime, we can map something F of B to F of B prime, and contravariantly for contravariant things. Here we can lift two functions, or two morphisms, one from A to A prime to A, from something upstream of A to the starting point. And so a starting point that's further out from A, we'll consider A prime. Get to that to A. And if we have something that goes from B to B prime, goes downstream of the destination of where we're considering, then we can turn something that's away from getting A's to B's, or away from getting from A to B, into away from getting A prime to B prime. So a profunctor lifting these two morphisms can take any way of getting from A to B into a way of going from A prime to B prime, a specific way for going A prime to A prime, from A prime to B prime, right? And it's notable that the first one is handled contravariantly. And we have something that we feed it something F that goes from A prime to A, but now we can go from A to A prime. You can transform this thing going from A to B to something that goes from A prime. And the second one is covariant in sort of a straightforward way. Okay. So here, this provides us this way of turning things going from A to B into things going from A prime upstream of A to B prime downstream of B. I tried to give some, intuition to what was going on with this, with these sort of diagrams last time. So if we know how to go from B to C, that if we have a specific way of going from B to C, right, just a specific way going from B to C, that will give us a specific way of going from A to D, for example. Namely, go this way or if I have a specific way from getting to B to C and a specific way from going to A to B here, and a specific way from going C to D here, that will give me a specific way of going from A to D. Anyway, follow this, go over via the designated way from B to C, and then down with the other. And that's exactly what lifting gives us here, away from going from, if we know away from going A to B, it gives us this way of going in that, and we have these two ways of going from the upstream thing to the starting point, and from the finished point B to the downstream thing. Then we have a way of going from that upstream point to that downstream point. Okay. I think this should be fairly familiar in your mind. And I emphasized how these profunctors can be thought of as bridges between categories, as establishing these bridges between categories. They are often applied to the same category, in which case it's an endoprofunctor. It's a profunctor occurring within a given category, from that category to itself, like an endoscope or an endoscopy. Endogenous thing, behavior generated within the model, right? But we can do this with different categories, and we'll be seeing that in just a minute here. This is a collage. I call it a montage. It's a collage. It's a collage. Okay. And these show these bridges from one category to the other. Each of these bridges, say from A to A here, the set of those is precisely the set that comes here from a given object here, from C, another object from C. This is the set of those bridges that go from a given object here to a given object over on the right-hand side here. Okay. And between any two pairs of objects, it could be a large set, an empty set, or some a small set between them. Here I happen to draw only one between any two pairs here, but there could have been several going from A to A here. Just like with the Hom profunctor, there could be several going from an object to itself. We will connect this back to the notion of representable soon, where the Hom profunctor will take center stage. But a lot of these basic ideas that we've been talking about with profunctors will carry over to help you understand representables and go on and understand the Oneida lemma, which involves exactly representables. Now, although it's not our point right now, I did note that in Brendan Fong and David Spivak's wonderful book, Seven Sketches in Compositionality, they have wonderful treatment of profunctors in the context of them being bridges, in the context of V-enriched profunctors to V-enriched categories where morphisms have this annotated piece of information. We keep track of the cost to go from one object to another, or the distance to go from one object to another. We might keep track, we might be interested more, can we go from one object to another? And in these contexts, profunctors are really useful. They're not only useful for knowing about the set of ways from going from, say, B to C or A to D. They're useful for asking about how much does it cost to go from A to D? Can you go from A to D? What are the different ways of going from A to D? And potentially, other questions. How reliable can you go from A to D, etc. We won't be going into that here, but it's a wonderful use in the modeling context. And in general, they're wonderful for reasoning about this sort of connectivity where we have these linkages and ways of producing one thing from another or getting from one place to the other. But today I wanted to bring us back some to double categories and also use it as an opportunity to reason about cases where these two categories are different. And there's some neat examples here. So some of you may recall the schema category for graphs, right? So where we have the schema for graphs, this is just not in double schema here. We're just dealing with a regular categorical schema like we dealt with last semester, right? In CATLab, for example, where we have V as an object, E as an object, and we have two morphisms from E to V, right? One called source, one called target. But we may have noted at some point how beyond this being a traditional used for CSets, where we map that, you have a functor from this schema into set, we might think of it as an atchit, as an AC set. So here we have an attribute type. Maybe it's a string, right? And we want to give every vertex a name. Or we want to give every edge a name. And so here we might have an attribute type, X. And there's going to be a way of finding out the name, the decoration, as we might call it, for a given edge. That's, you could be excused for thinking it's like a kind of like a different sort of hum, going from edges to this piece of information. Maybe it's strings. And there's one for a decoration for vertices as well with the same type. Say it's right. So there's a story for this, which you can find on this blog post, the categorical scoop on attributed CSets. And it has double categories and profunctors writ large within that blog, and I'd encourage you to look at it. I'm going to present some of the essentials on it here. as an example of a profunctor. So here we're going to have one category, C, and another category, D. And we're going to have a profunctor. We're going to have profunctor between them. Okay. And this profunctor, I'm seeing something in the chat. Yes, Bartosz Muliski has some good examples on profunctors. Bartosz likes to describe them as proof-relevant relations. Is something that he likes to describe. They're ways of relating these two categories, and I think it's a good way for thinking about it. So we have category C, kind of the schema category, and category D, the category of data. And we have an object in the category of data. And then we're going to consider this profunctor, okay, that goes between them, this attribute profunctor. And the attribute profunctor for a given pair, one from an object from C and one an object from D, is going to have a set associated with it, right? Remember, a profunctor is a functor from C-op, the objects of C-op are just the objects of C. So it's a functor from C-op cross D. The objects of D here is data, so this is an object from D, to set. So there's a set of these things which are shown in this kind of this evocative ellipse. And there's a similar one from V to X, right? And what's shown here is a collage, right? You'll recognize these bridge heteromorphisms, as we call these bridges from E to X. And the most basic kind of the generators of these are this E deck, which goes from E to X, right? And there's V deck from V to X, here, shown. And those are characterizing that X is a attribute for V or an attribute for E, right? We have a name, a string for vertices and edges. But beyond those, we have this precomposition up with upstream things for over here in C, and with downstream things in X, of which there are none. This is shown as a discrete category where there are known, where each object has no morphisms to other objects. They're solitudes. They can have morphisms to themselves beyond the identity, but it's a discrete category. So beyond E deck, the ones from E to X include target and then V deck. The ways of getting, remember this idea is the ways of getting from, we can go here from B to C, for example, directly with this green arrow here. But we could also get to B to C if we can get from C to C and then go from B to C here. So we could go B to C and then C to C. And so it is over here, right? The ways of getting from E to X do include a direct connection with E deck, but it also includes a connection from V to X and then providing you can get from E to V. So if you go with target from E to V and then over with V deck, that's a way of getting from E to X, right? And perfunctorily, we keep track of that. That's the whole, being able to lift, right? Being able to lift here from something from getting A to B to something that goes from A prime to B, or even from A prime to something downstream of B, including B itself. So that's part of the profunctorial logic, the actions allowed by the profunctor, the actions it can undertake is this precomposition action. That gives us another bridge from E to X. It generates that bridge, right? And there's another one too with source, right? We can go with source over, again, the semicolon. It's like the fat semi, do this and then do this over and then over like this. And that's also a bridge from E to V. And that's part of what profunctorial logic captures. So these are all ways of going from an edge to a string. One is you could look at its string, its name directly, or you could get its source of that edge and get its name, or get the target of that edge and get the name of that vertex, right? It may be worth reflecting on that this is somewhat non-standard notation. It's like we're kind of taking a composition of something that's an honest to goodness edge here in C with something that's a bridge, which might strike you awkwardly. We're going to see that's very common to think of it that way, and we're going to see this comes up in the Cacolet context. For example, composing a link with a flow, which is a, admittedly intriguing idea. But, if you want to unpack that a bit, you could say, well, look, VDEC is an attribute, attributive. There should be V comma X, not E comma X. Oh, sorry. And then if we consider the attributes for target and IDX, we get these are morphisms like F and G as I described them here, F and G. We're lifting those. We lift those, and that gives us something that maps from this thing from A to B to something that can map from something upstream of A and something downstream of B. And so having done that, we get this thing that can map something from A to B. Well, then we can go from place something that can go from A to B, V and V to X here with VDEC, and we get something that can then go from E to X. This is the precomposition side, the F side. So remember that this lifting gives us the ability to map this to this, right? It's just like lifting something that goes from instabools to operate on lists gives us something that can map from lists to list events to list on bools. And so it is here. By lifting it, we get something that can take any element of this, a way to get from A to B, and it will turn it into a way to get from A prime to B prime, using F and G in the meantime. And that's exactly what's going on here. This is our F, this is our G, and we apply it to a way to get from V to X, and that gives us a way to go from E to X. Okay. So this provides a glimpse of how profunctors here are used, the profunctorial story behind attributed CSets. We have relational data on the left, things like, where we have a set of edges and a set of vertices, and, we're not terribly vested. I mean, we don't particularly care about what we call edge one compared to edge two. It's whether we call it this one edge one or edge two, edge three, it's all relational data. that it doesn't matter what we call it. What matters is the role it plays, right? Vis-a-vis vertices. And as long as it's the same role that it plays, we don't care if we call it edge one, edge two, edge three. But then we have this other world of data where we really do care. What's zero, what's one, what's two, what's 3.14159, whatever. And um, and we have these mappings between the two. So if you have people over here and they have the relationship, and, or maybe these are people here, and these are connections between people. Who you call person one, person two, person three is irrelevant, but you care about their age, you care about their income, you care about their education level, you care what province they're in. And that's where this data would live. And so we can give people attributes phrased in terms of these attribute types. We care about their names. And this is the way we can keep that information. This is relational data. This is attributed data. Any questions on this before I go into another example of profunctors? This is one profunctor story with two different categories here. Any question? Okay, not hearing any. Um, oh,
For
mm-hmm,
I
mm-hmm,
just thinking about these to the IPV model. Can we imagine victims are as a age like V and those incidents, abusive incidents,
mm,
and we can assign the attributes like fear, trust,
mm,
and like
mm.
support that
Right.
supportive things to both victims and those
That's right.
abusive incidents.
That's right.
And
Yeah. Yeah. I think that's a good idea. Yeah, because those would be more attributes. A given incident might involve a victim and then a different perpetrator to that
yeah.
victim, but there'd be information about that incident that you might want to keep track of, like where it occurred. Well, maybe, when it occurred, the time, or how severe it was, which is not relational data. It's more attributed data. And then some information about the victim or the perpetrator that you'd also want to keep track of. Yeah.
Okay, thank you.
Yeah. Great question. Um, so another view of this, which I'm going to spend a bit less time on because I do want to hit on a few examples. This is actually discussed further in that article, and this is more specific for, well, as I understand it, sort of the context of this idea of um, attributed C-sets as having um, a database representation, and here we can think of we have a plain old C set that's shown here on the right, a mapping from a schema category C to fin set. And then we have this profunctor, right with this slash here, which gives some data for um, some data type or excuse me, um, some particular sort of attribute type to to just some objects. So there's a relation. Remember Bartosz-Miller's nuclear proof relevant relations. There's this relation between C and data. There might be for a given object no attribute type needed. For some objects, there might be attribute type. I'm not sure there ever be more than one though. Uh, and uh, and in fact, well, no, there could be because what this is denoting is like maybe C has maybe an object C has a person's name and a person's age, for example. Um, and so like a given attribute here might be for a given object of this and a given data type, there might be like a source, um, uh, or the decoration and the weight of the edge or something like that. And then each of those can be thought of as mapping to a set of possibilities. So like the attribute type might have true and false as its possible values, or in other cases might have all possible strings. And this might associate it with a particular Julia type. And then there's a mapping from a given finite set, so like the set of people, to a column of, let's say, double values representing their age, or a column of whether or not they're enrolled in the program, or a column of their names. So this sort of construct here basically takes a set and it induces for a given Julia type a column of the required length of the size of the set, a column of the appropriate type for the attribute for name. Maybe it's a Unicode string. So it's a column of Unicode strings, one for each of the people here. You can again find this in the categorical scoop on attributed C-sets as a way to think about attributed C-sets. Okay? And this is just a C-set, and this gives them some attributes. So that's another way of sort of thinking about this mapping in the database context where you have like columns, for encoding things. I did, though, want to have an example that maybe is a bit close to home for our uses of Cat Colab and relates to functionality already in there. So you folks will remember the C-set, the Capricci for schema category for causal loop diagrams, right? We have a variable, we have L plus and L minus. And I'm going to put aside here the attribute side and just consider it as a C-set, not an attributed C-set, not giving variables names. We can deal with that separately. But here I'm going to treat it as a C-set because this is going to get back again to this idea of double theories and double models. And I'm going to emphasize this because it's going to play a sizable role in how Cat Colab works with double theories and double models of those theories to encode information, in this case about causal loop diagrams. So this was our schema in C-sets. And you remember that the slogan I introduced, and it was a wonderful one from Evan, he said, look, well, CatLab has, for a schema category C, you have a set, and your focus is on C-set. It's useful as a slogan to think about Cat Colab for each schema category, for a model of a schema category, instead of giving you a C-set, a database, giving you a C category. So instead of each object becoming like a set, a table, a set of variables, right? A set of variables, or a set of plus links, a set of minus links. Instead, each object in your schema, in your double theory, becomes a category. It enacts the causal loop diagram. And that's what we have here. And you may remember this, and we're going to continue to struggle with it, that, this is the double theory for causal loop diagrams or signed categories. So here a given object turns into a category. What does that category represent? Well, it represents the causal loop diagrams. The objects of the category, this is a regular category. This is not a double one on the right. There's a double category on the left. But a lax double functor maps each object here on the left into an object on the right. And that object has some objects in it on the right, right? The category associated with V to which it maps, not a set, but a category, has more structure than we would have with a CSet. We don't have a set of coming from this object when we map it. It's we're mapping it to span, and through lax double functors and compositors and so on, we get a category. Each object of that category encodes the variables of our causal loop diagram. And we have morphisms between those objects, which are encoding the links between those variables. And part of the amazing thing here is that we have this latitude to describe not just one type of link, which you might be excused for thinking, well, if this is a category on the right for a causal loop diagram, that's kind of nice, but how are we going to have plus and minus links? Well, we can do it. We can encode plus and minus links. And how do we encode it? We encode it, ladies and gentlemen, through profunctors. Okay, so how are we going to do it? Well, I told you once that like the identity pro arrow here has associated with it the positive links in this category, the positive arrows in this category, positive morphisms in this category. And this pro arrow kind of has associated with it the negative links in that category. But I didn't really explain another view of this, which is very important, which is a profunctorial view. Very valuable, and actually particularly valuable to keep in mind in some cases. So we're going to see why this is. And I'm going to take a particular diagram to be encoded, this one here, this here one. We're going to have two positive links in this sort of upper positive feedback and three negative links down here.
Sorry, we haven't any slides.
Oh, you don't see slides?
No.
I see the slides.
I see the slides.
Oh, I haven't.
So I know in Zoom, sometimes you can say like modern Zoom clients, you could say like, see, Nathaniel has good slides versus like, look at his face, which I wouldn't recommend. But there may be a separate tab up at the top where you see you'll see my slides.
Okay.
Yeah. Okay. So this is the causal loop diagram to be encoded. We have three negative links, two positive links. And what I'm telling you is this is a useful way to think about this situation. We encode this and we just label these pluses and minuses. But really what's going on at a finer grained level, at a more granular level, it's about profunctors. So each object in this theory turns into a category, a plain old category. No magic here. The morphisms aren't labeled by plus and minus. No. They're just plain old morphisms. Each object turns into that category. The pro arrows here turn into profunctors. In fact, that's why they have the name pro arrow. Each of them turns into a profunctor. Now, it turns into a if the pro arrow goes from one object in this theory, object A to object B in the theory, the profunctor will go from the category associated with object A to the category created for object B. Remember, each object turns into a category. So if you have a pro arrow from the object A in the in this double theory to object B in the double theory, each of them will, well, each of those objects will turn into a category, and the pro arrow will become a profunctor between those categories. And that's what I've drawn here. But each of these pro arrows goes from this object to itself. So it's an endo-profunctor. It's a profunctor from that category, the category into which V turns, into a, so V becomes a category, into that same category. Okay, so here we are. This is the category that V turns into. Here's our double theory. I say for sign categories, it's also for causal diagrams. You can call it either one, double theory for causal diagrams. Okay, so here's this object turns into this category. And we have a profunctor that's Z mod 2 here, Z sub 2, which I've shown is a collage. Okay, it goes from the category associated with this object to the category associated with the object. So this is the same category. But it, as a profunctor, it has these heteromorphisms. And then you might be excused for saying, wait a minute, there's this other profunctor, the identity profunctor. Well, that's the Hom profunctor. That's the standard profunctor that every category has. So I'm just going to draw that arrows in that category. They're just arrows in this category associated with V, into which V, is with which it's associated, or as mathematicians like to say, to which it is associated. So the lax double functor turns V into this category, and they're the kind of morphisms of that category, V, I'm just going to draw like this, even though they're the Hom, they're from the Hom profunctor conceptually, but they're just Hom sets, right? Going from smoking to nicotine addiction, or nicotine addiction to smoking. The key thing is they're not labeled by polarities. No. Nothing's labeled by polarities here. I'm telling you, these labels by polarities is a nice way to kind of informally think about it. It's kind of a nice heuristic. But in this category, it's just a plain old category. There's no pluses and minuses. Well, what there is are these ones from the Hom profunctor, which are in the category. And then there are these ones associated with this Z2, the mod 2 profunctor, these heteromorphisms. And the role played is different for these ones in the category. These become the positive links of this category, plus plus. Those are the positive links of this category, the ones from this Hom profunctor. The ones that are the heteromorphisms that are associated with the profunctor between these, from this category to itself, like from smoking to health, become a negative link from smoking to health. That's what it encodes. That's how we encode negative links. They're the heteromorphisms, the bridge morphisms induced by this Z2, this mod 2 profunctor. So there's one from smoking to health. That's this negative link. There's one from health to commitment to cessation, health to commitment to cessation. That's this negative link. And there's one from commitment to cessation to smoking. That's this negative link. So here we can informally think about it as like creating a category with different labels for the morphisms in that category. But really it's coming from the fact that each profunctor has heteromorphisms, and that's a different breed of link, right? And in these ones here are one breed of link, the plus ones here, and for each profunctor here from this object to itself in this category, endo-profunctor, we have a different breed, a different, labeling. And here are the minus links. If we had ones that were unknown U link, we could encode that with a different self-profunctor. So this is how we can associate this sort of labeling these different breeds of links. Each is associated with a different endoprofunctor, a different endo-pro arrow in the theory because it has heteromorphisms that connect this category to itself. We could think of it as having these links. And key, absolutely key, because any profunctor supports pre-composition and post-composition. We can compose those links. Those, you might say, well, they're two different types of links, so they can't be composed. No, they certainly can be composed. You can compose this link here, nicotine to smoking, to this link from smoking to health. And in fact, that link from smoking to health to this link to commitment to cessation, and commitment to cessation to this link from smoking. You can compose these plus links with these minus links. And not only that, you will, because of the rules associated with profunctors, you will end up getting the right type of link that you can get out as a result of this composition. So a minus and a plus, giving a plus, etc. This ends up coming from the rules for profunctors. The fact that we can mix these is because we can pre-compose, these bridges, these heteromorphisms with arrows upstream from here or downstream down here, etc. Okay, so this is another glimpse of how double theories, double models use profunctors in a key way. And just as we said, each object turns into a category, each pro arrow turns into a profunctor between said categories, where one of them is just the Hom profunctor, so it's just kind of the standard vanilla type, in this case, plus arrows. But otherwise, we get profunctors, which have heteromorphisms between categories. Had I more time this time, I might talk about, for example, the schema, the schema category for database, the double theory for databases. And we could see how that encodes things in this sort of way, where we have a one object to encode that becomes the data category, one object that becomes that is the category of objects, normal category of objects and morphisms, and where you have heteromorphisms between them in CATLAB. And one important difference is here, it wouldn't be a discrete category. It could be, you could have links between these data types. Like over here, there could be a link from int to double, or int to bool for is prime, and a link from int to bool for is even, another one for is odd, or a link from, string to int for the length of a string or what have you. So in other words, this would be a category, this would be a category, and there's a profunctor between them coming from a pro arrow in that theory. So that theory for databases would have two objects, one for kind of the relational data, one for the attributed data, and a pro arrow from the relational data to the attributed data. And it would lead to two categories. And a profunctor between them, much like this. Okay, that's all we have time for today. I've got to hop on to another meeting. I hope that was helpful, and I'll seek to post my slides in the forum. Thank you, everyone.